Welcome back to the Networking Mastery series. This is Stage 4, Lesson 28. Today, we're digging into two classic distant vector routing protocols, RIP and EIGRP. The big idea tying them together is what engineers affectionately call routing by rumor. Routers making decisions based entirely on what their neighbors tell them. By the end of this lesson, you'll see exactly why that approach is both elegant and a little dangerous. So, here's the roadmap for the next few minutes. We'll start with the core mechanics of distance vector, how routers actually pass knowledge along to each other. Then we'll meet RIP, the original hop count protocol, before stepping up to EIGRP, Cisco's much smarter take on the same idea. And finally, we'll tackle the elephant in the room, routing loops and the clever tricks these protocols use to keep your network from eating itself. Let's start with the core idea. Picture three routers in a line. R3 owns network X, and it tells R2, hey, X is one hop from me. R2 trusts that, adds itself into the path, and turns around to tell R1, X is 2 hops away through me. And here's the key insight. R1 has no idea R3 even exists. It only knows what R2 whispered to it. That's routing by rumor. Each router only sees as far as its neighbor's word and just trusts and relays it down the line. And the classic example of routing by rumor is RIP, the Routing Information Protocol, born back in 1988. It uses the Bellman-Ford algorithm with the simplest possible metric. Just count the hops, and anything beyond 15 is considered unreachable. Every 30 seconds, each router shouts its entire routing table to its neighbors over UDP port 520. On Cisco, turning it on is just a handful of commands. Enable RIP, pick version 2 for classless support, advertise your network, and disable auto summary so your subnets don't get collapsed into a 8. So if RIP is so simple, why do we barely see it in real networks today? 5 big reasons. That 15-hop ceiling means anything larger than a small office is off the table. Convergence is painfully slow. When a link dies, it can take minutes before R1, R2, and R3 all agree on the new reality, and during that window traffic just gets black-holed. The metric itself is naive. RIP would happily pick a single hop over a 100 meg link instead of 2 hops across 10 gig fiber. Add in those full table broadcasts every 30 seconds, chewing up bandwidth and CPU, plus a long history of loop problems patched over with split horizon, poison reverse, and hold down timers. And you've got a protocol that's really just band-aids on a fundamentally limited design. Enter EIGRP, Cisco's answer to all those RIP shortcomings. Born proprietary back in 1993 and finally opened up as RFC 7868 in 2016, it's still a distance vector at heart, but a much smarter one. Instead of hop count, it uses a composite metric that actually factors in bandwidth and delay, so R1 will correctly prefer that 10 gig path. Updates are triggered and incremental, no more chatty 30-second broadcasts, and thanks to the dual algorithm, convergence drops from minutes to sub-second. On Cisco gear, configuration is refreshingly simple. Pick an AS number, declare your networks with a wildcard mask, and turn off auto summary so your subnets stay intact. So what does that smarter metric actually look like? At its core, EIGRP multiplies 256 by K1 times bandwidth plus K3 times delay, and those K values are just tunable knobs that decide which factors count. By default, only K1 and K3 are on, meaning EIGRP looks at the slowest link in the path and the total delay accumulated across every interface. Load, reliability, and MTU are all available, but they sit at 0. Switching them on can cause instability, so in practice, almost nobody touches them. Now here's where EIGRP really pulls ahead of older protocols. Picture R1 trying to reach a destination through 2 neighbors, R2 with a metric of 100 and R3 with a metric of 200. R2 wins, so it becomes the successor and gets installed in the routing table. But R3 isn't discarded. It's stored as the feasible successor, a pre-computed backup sitting quietly in the topology table. The moment R2 dies, R3 takes over in milliseconds with no recalculation needed. That's the secret to EIGRP's near-instant failover. So let's put these two protocols head-to-head. RIP, born in 1988, leans on Bellman-Ford, counts hops up to 15, and floods its entire table every 30 seconds, which is why convergence drags on for minutes. EIGRP, 5 years younger and now open since 2016, runs dual, blends bandwidth and delay into a richer metric, sends only incremental updates, and converges in under a second thanks to that feasible successor we just met. Same distance vector family, worlds apart in sophistication, which is why RIP lives in labs, while EIGRP still runs real Cisco networks today. Now, that loop problem we keep hinting at, distance vector's classic Achilles heel. Protocols don't just ignore it. They stack 5 defenses. Split Horizon says if R2 learned about network X from R3, R2 must never advertise X back toward R3, kills the rumor at its source. Route poisoning flips the script. When R3 loses X, it shouts X is at 16 hops, unreachable. A poison pill so neighbors can't keep believing it's alive. Hold down timers, then freeze that bad news for about 180 seconds, ignoring any router that suddenly claims, wait, I have a path. Triggered updates fire instantly on change instead of waiting for the next 30-second cycle, shrinking the loop window. And TTL is the last line of defense. Every rotor decrements it, and at 0, the packet dies, capping the damage at 255 hops even if everything else fails. So, with all that defense machinery in mind, here's the honest practical question. When would you actually reach for each of these? RIP, frankly, lives in 2 places now, your ccna exam and tiny legacy setups. If you've got more than 15 routers or anything built this decade, walk away. EIGRP still earns its keep in pure Cisco shops that want sub-second convergence and simple config, think medium enterprise WANs. But the moment you mix vendors, it's out. And OSPF, which we'll dig into next, is the industry standard, multi-vendor, large campus, ISP backbones, anywhere you need a full topology view. That's the IGP you'll meet most in production. So let's pull the whole lesson together. Distance vector is routing by rumor. R1 trusts what R2 whispers, R2 trusts R3, and the network converges on faith. RIP is the original, simple, capped at 15 hops, painfully slow, and mostly a museum piece today. EIGRP is Cisco's smarter take, using dual and a composite metric to converge in under a second, with feasible successors sitting ready as instant backups. And tying it all together, the loop prevention toolkit, split horizon, route poisoning, hold down timers, and triggered updates keeps the rumors from spinning out of control. And here's your cheat sheet, the whole lesson on one page. Keep this handy. RIP fingerprints are hop count up to 15, full table broadcasts every 30 seconds on UDP 520, and an administrative distance of 120. EIGRP's signature is dual, that bandwidth and delay composite metric, IP protocol 88 riding directly on top of IP, and an AD of 90 internal or 170 external. If you remember those numbers, you can identify either protocol the moment you see it in a routing table. That wraps up distance vector. Next up in lesson 29, we're shifting gears completely into OSPF, a link state protocol where instead of trusting rumors from neighbors, every router builds its own complete map of the network. It's a whole new way of thinking about routing, and I'll see you there. If this lesson helped, hit subscribe at youtube.com. Ciao, Dargslan, and I'll catch you in the next one.